Hello again. One of the things that we have to think about when we're writing redox reactions is that some of them will happen all by themselves. You just combine the chemical species, and as soon as they touch, an electrochemical reaction begins, and others won't. There are some reagents that you can combine, and they just sit there and nothing happens because the reaction is what we call non-spontaneous, meaning it won't happen by itself. So to tell the difference, we need some information out of our data book, and specifically, we need the table of selected standard electrode potentials on page 7, which we often just call the redox table. And so we're going to be pulling numbers out of that as we work our way through this. The questions that they give us are just, here are some mixtures that contain either pure substances or ions or some of each. And the question for each of these is, will anything happen if we put these two species in contact with each other? So let's see how these questions look. The first thing that has to happen when you're given one of these lists is just write out all the species, make sure you understand what's there. A says we have nickel metal and a solution of silver ions. So nickel, you could write solid here if you want to be really clear about that. And silver is Ag, the ions are plus, and it's probably safe to assume those are in aqueous solution. So if we have those two substances and we want to know what they're going to do, if anything, when they're mixed, we go over to our redox table, and we're going to be looking for nickel and silver ions. The way this works is, first we're going to read down the left side of our redox table, looking for our strongest oxidizing agent. All of these things on the left side, this, all of these are oxidizing agents, and the strongest one on the entire list is fluorine gas. Then they go weaker, 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 and down at the extreme bottom is the weakest oxidizing agent. So our scale here is from strongest oxidizer to weakest oxidizer. We're trying to find the strongest oxidizer that is present in our system. And so going down this list, remember we had nickel metal and silver ions. I'm just looking for either one of those. So fluorine, no, don't have that. Lead oxide, no. Acid permanganate, no. Gold, no. Perchloric acid, no. Chlorine, no. Nitrous acid, acid dichromate, no, no, no. We're looking for nickel or silver. No, 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 yes. Silver ions right here are the strongest oxidizing agent in this first setup. So one of our reactions is going to be silver ions picking up electrons and turning into silver. Now that we have that, the second part of this is start on the bottom right corner of the table and read up. On this side, the strongest reducing agent, lithium metal, is in the bottom right corner here. And if we don't find that, we'll try potassium, barium, calcium, da. We'll work our way up the table, and this table goes from strongest reducer at the bottom right to the weakest reducers, weakest reducing agents in the top right corner. So let's see how long it takes us to get a hit here. Again, remember the things that we have in our system are silver ions and nickel metal, so we want to find one of those things. So lithium is not silver or nickel, neither is this. No, 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 no. We want nickel or silver, nickel or silver. This is interesting for a second, but it's not silver ions, it's silver solid, and we don't have the sulfur either, so that wouldn't work. No, 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 no. Yes. Nickel metal right here is our strongest reducing agent. So one of our reactions would be starting on the silver ion side and going to the right. This other reaction would be in reverse because we'd be starting on the nickel side and going to nickel 2 and 2 electrons. That's all right. Normally one of these reactions is in the reverse direction. And finally, the way you tell if these reactions are spontaneous is actually pretty simple. If you draw an arrow from the strongest oxidizer to the strongest reducer, if that goes downhill, if it goes in this direction, we say our reaction is spontaneous. Anything going this way is spontaneous. Anything that goes uphill is considered non-spontaneous. The idea is reactions that go this way have some stronger electron attractor, taking electrons away from a weaker one, which makes sense. This direction would mean something weak is ripping electrons off of something stronger, unlikely, and so we'd say these reactions do not happen unless we help in some way, and we'll show you how to do that later. So for now, you can think of it as downhill is spontaneous, uphill is non-spontaneous. There's another way to calculate this later where we use cell voltages, which we will definitely get to. I actually like that way. But for now, downhill and uphill will do us. So that took a long time. Let's see if we can knock off a few more reps of this and get comfortable with it. This out of here. Sorry, I won't clutter this up so much with my next attempts, so this part will all go faster. So remember again, we want to find our strongest oxidizer, read down the left to find your strongest oxidizer, read up the right side to find your strongest reducer, and then connect the two of them with an arrow, and if it goes downhill, spontaneous. If it goes uphill, non-spontaneous. So let's get good at this. For the nickel, metal, and silver ions, we can say that reaction is spontaneous. Next one is zinc metal in aluminum ions. All right, back to our table. Zinc metal, aluminum ions. So our two things we're looking for are zinc solid and aluminum 3, which we presume will be aqueous. Zinc or aluminum. So no, 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 no. I know zinc and aluminum are on the bottom half of the table, so I'm doing this part a little fast, but if you're not really familiar with the table, just be patient, go one line at a time. No, no, no. Zinc, aluminum, zinc, aluminum, zinc, aluminum. No luck yet. Zinc, aluminum, zinc. Ah, here we are. Now, bad news. This is zinc ions, and what we have is zinc metal, so this is no good. You have to be picky about this. If we say that zinc metal is in the solution and you find zinc ions, this is not a match, and your search continues. Water, chromium, selenium, sulfate. Here, aluminum ions. These would be our strongest oxidizing agent. And this reaction, boxed in red, would happen forwards. Aluminum ions will pick up electrons and turn into aluminum metal. Now that we have that, we read up the right side, again looking for either zinc metal or aluminum ions, and we'll see what our strongest reducer is. So lithium, potassium, no, 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 no. We don't have aluminum metal, so this doesn't mean anything to us. We had aluminum ions, which we already used, so no interest there. Sulfite, selenium, chromium, hydrogen, zinc. This is our strongest reducing agent. And so, if we do a line from our strongest oxidizer to our strongest reducer, what does this mean? arrow going uphill means this reaction is not spontaneous, meaning if you put zinc metal in aluminum ions, nothing should happen. There's a hypothetical reaction where aluminum ions turn into metal and zinc oxidizes to zinc ions, but that reaction won't happen by itself. We'd have to help it. It's like a rock rolling uphill. Rocks can roll uphill if you push them, but they won't go by themselves. They need to be pushed. So, second one, non-spontaneous. We can go back to B, and we can put non-spont. Next one, aqueous mixture of copper 2 ions and iodine ions. Copper and iodine. Iodine if you're British. Okay, so we have copper ions, we have iodine ions. They said that was an aqueous mixture, and I'm pretty sure in this question they intend us to just think about the copper and the iodine. Technically, when they talk about an aqueous mixture, that tells us water is in the system too. So later on, this will be more important, but I'm going to put water in just in case. And we'll see if that comes up when we're doing our search. So we're looking for copper ions, iodine ions, or water. Starting on the left, reading down, looking for our SOA. Copper, iodine, water. Nope, 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 nope. Copper, iodine, water. This is iodine, but it's solid iodine, not the ions, so this does not interest us. Or you might pause here for a second and just make sure, but I minus is not the same as I2, so the search continues. Here, copper 2 is our strongest oxidizing agent. Good. So now we can start searching for our strongest reducer. Again, copper, iodine, and water are the things we're looking for. I'll switch to blue because I've been doing that. Copper, iodine, water. Copper, iodine, water. Sorry, I kind of have to repeat that to myself just to hold it in my brain while I'm doing this other thing. I hope that isn't ultra irritating for you. Copper, iodine. Here's iodine, but we have no silver, so that's irrelevant. Copper. We don't have copper metal, so this is no good. Search continues. Here we go. Iodine ions are right there. These would be our strongest reducing agent. And what do you think this means for the spontaneity? Strongest oxidizers here, strongest reducers here. Draw your arrow, and it's uphill, which means not spontaneous. If you mix these two ions, nothing should happen unless we give them a push. I'm guessing you kind of get the idea now, so I'm going to speed this up a little bit just so you can quickly see the answers for the rest of these, or pause this, try the remaining ones yourself, and then we can talk in a minute and see if you agree. All right, D, chlorine gas in a bromine ion solution. Over to the table. Chlorine gas and bromine ions. I'm also going to start finding things a little faster here because you don't have to watch me scanning the table all day. Chlorine gas right there. Bromine ions. Well, I thought I knew where those were. Where the heck are they? There we go. Bromine ions. Downhill, spontaneous. Chlorine will react with bromine ions. Next one is an aqueous mixture of copper 2 and tin 2. This is E. Copper 2 and tin 2. Copper 2, there we are. That'll be our strongest oxidizer. And tin 2. Watch out, you've got tin metal here, and then you have tin 2 right here. So, downhill, spontaneous. Copper ions will react spontaneously with tin 2 ions. Copper metal in nitric acid. Okay, now they're getting a little cute. Let's see what that means for us. This is one where if you haven't thought about Chem 20 in a long time, you might get shaken up a little bit. Copper metal, easy enough, copper solid. Nitric acid, if you look it up somewhere, you're going to find HNO3. But remember, the thing acids do is dissolve in water and release hydrogen ions. And nitric acid is a strong acid. It's one of the top 6, meaning it's very good at that. It dissociates 100% pretty much instantaneously. So when you get a bottle that says nitric acid on it, even though the label says HNO3, what you're really getting is a bottle of hydrogen ions and nitrate ions floating around in water. So, weirdly, a bottle labeled HNO3 contains no HNO3. It contains these things instead. Acids are very active. They dissociate and release hydrogen. So, when we go to our list, fluorine, lead oxide, we don't have any of those first few things, perchlorate. You won't find HNO3 on this list, but what you are going to find right here nitric acid brings both of these things. A nitric acid solution has NO3 ions and it has H plus ions, and these two working together, that team is our strongest oxidizing agent. So the nitric acid shows up there, and copper metal is right below it. So we get a spontaneous reaction between those, which in short means nitric acid will burn holes in copper. Nitric acid will also burn through lead, tin, nickel, cobalt, any metal that's lower than it. So all of these things that give downhill arrows will produce a spontaneous reaction. Are there any metals that nitric acid can't eat through, you might ask? Well, anything up here, right? If it's uphill, that means the reaction's non-spontaneous, which means nitric acid wouldn't be able to do anything to that metal. Now, a lot of these are weird chemical solutions that aren't metals or aren't solid in the case of mercury, so that's no good. But there is one. Gold. Turns out if you need to store nitric acid and you don't want to use glass or some kind of polymer, it turns out gold metal can resist nitric acid because the reaction between them is non-spontaneous, which means put nitric acid on gold, nothing happens. But the question was, if you put nitric acid on copper, will something happen? And the answer is, yeah, downhill arrow means spontaneous. I keep promising to do these faster and then I get chatty. Sorry about that. I promise to be businesslike for the last few. This one is spontaneous. Silver in an acidified solution of permanganate ions. Okay, so we have silver metal. Put a solid on that if you like. Acidic permanganate. Acidic means we have hydrogen ions, and permanganate is MnO4 minus. And if you start looking for those, you get a hit very quickly, actually. Acid permanganate, meaning permanganate ions in an acid solution, are a very strong oxidizing agent, third highest on the whole list. So they together are our SOA, and silver metal is right there. Arrow going that way means spontaneous. Acid permanganate will burn holes in silver metal given time. This one is spont. And last one, copper 2 ions in water. Clear away the old stuff. Okay, so we have copper 2, we have H2O. If you read down the left, copper 2 is right there. That would be our strongest oxidizing agent. Reading up here, we're looking for copper 2 or water. No luck, no luck, no luck. Here's water, but it's with sulfurous acid, so that's no good. This is H2O2, not water. Hydrogen peroxide, still no good. Here's water with N2O4, no good. Here, 2H2O. This is water by itself. Water is a reducing agent. It's not a very good one. It's near the top of the list, but it can react by itself. And down here, just in case this ever comes up, water can be an oxidizing agent too. And again, it's not great at it, but sometimes if you've blown through all this section and you haven't found an oxidizer, water will step up. In this case, though, strongest oxidizer wants to be copper 2, strongest reducer wants to be water, and arrows this way tell us non-spontaneous reaction. So nothing exciting happens if you put copper ions in water. That reaction would be non-spontaneous.